We have more than 100. I think we can begin immediately, actually, because we have a lot of things to cover today, and there are two quizzes. So, all right, let's begin. So, welcome to week 11 of AI504. So, this week is Transformer, and this is probably the most important week in all weeks in the entire semester, because everything, as I said in the introduction, the very first class, everything these days is run on Transformer, except for image synthesis or image generation, which runs on diffusion plus Transformer. So there's still Transformer playing a role in it, but diffusion is another thing we're gonna learn anyway. But still, besides that, basically everything runs on Transformer. So if you're not familiar with it, you're not gonna understand much of what's going on these days, because almost everything is just a variant of Transformer. Actually, that's a little bit more accurate, I guess. A variant of everything is like a variant of Transformer. So pay very careful attention, and yeah. So project 2 and 3, that it'll also run on Transformers. So yeah, if you have any question during the class, just don't hesitate, because this is probably the most important thing we're going to learn. All right, so we're going to first start with self-attention. All right, so yeah, it's fast enough. All right, so we're going to start with self-attention, then a little bit of a bit of extension to multi-head attention, and then we're going to talk about Transformer, the encoder side, because Transformer is actually a sequence-to-sequence model. So usually when people say Transformer, they either mean the encoder side or the decoder side, but actually the Transformer, the very first paper, it was proposed to run a sequence-to-sequence model, then something called positional encoding, and then the final one, the sequence-to-sequence transformer, and a mask self-attention. So that will be it. All right, so what is self-attention? So we start with self-attention. So if you did not understand attention in the previous week with the RNN and attention with sequence-to-sequence and all that, you're not gonna catch up with what I'm going to say today. So, so if you don't understand, just please, ask questions. All right. So self-attention. What is self-attention? So, Transformer, the paper, came around in 2017 from Google, so the language team. So actually, a lot of things we use today in the machine learning, the field of machine learning, we owe a lot to the translation researchers, because the very first RNN sequence to sequence with RNN was proposed to do translation. Again, attention was proposed to do translation. Transformer was proposed to do translation. So a lot of things we owe to the translation researchers. So the name of the paper is "Attention is All You Need." It's kind of like a parody of "All You Need Is Love" by Beatles, the song. So the core idea is, let's use only attentions to handle sequences. So in RNN, it's by design, RNN was able to handle sequences because there's a for loop going on. So the way that RNN encodes sequences is one token at a time, one term at a time. Like if we have like 5 token input sequence, then we've first put the first token into the RNN, then the second token, the third token, fourth token, fifth token. So you need to run a for loop to encode sequences using RNNs, because it's by designed to handle sequences. But the core idea of Transformer in the paper, "Attention is All You Need," is let's not do that. Let's not use for loop anymore. Let's not use for loop, and let's just use attentions only. So the reason that the Google researchers proposed Transformer is because they didn't want to use for loop from the beginning, because the for loop was the thing that slowed everything down. Because if you run a long sequence, if you want to do a translation on long input sequence, or long text or long documents, then it means that, for example, if you have 200 tokens in your input, you need to run the for loop 200 times. So it's going to take a long time. And Google needs to serve all around the world. They need to serve like hundreds of different languages to like billions of users. So they didn't want to use RNN in doing, translation. So that's why they said, okay, let's not use for loop, but we have a lot of GPUs because Google has a lot of GPUs. We have a lot of GPUs, so we can do a lot of parallel processing. Like matrix manipulation, matrix multiplication, like basically matrix-based operation. They can do it pretty efficiently because they have a lot of GPUs. Let's somehow forget about the for loop and just deal with attention and try to maximize the efficiency of their GPUs. So the core idea is if you have a input sequence such as I like going to movies, termination symbol, the dot symbol, then the way that you still need to tell the model that it is a sequence. So you can't just put I in separately, like separate. You can't just, independently treat them and then somehow aggregate. You can't use MLP to, turn this into a vector, turn this into a vector, turn this, and then somehow concatenate them all or sum them all. You can't do that because you still need to tell the model that you're dealing with a sequence. So the idea is, why don't we use attention, but at each term, each token takes a turn to be the center of the attention or the center of the attention giver, actually. So when it's the eye's turn, it looks around what is around it's in the vicinity. So the like token is right next to I, going token is next to I, and then 2 is like three positions apart, four positions apart, 5 positions apart. So that's what's going on when I is the main character. Then it's the like's turn to be the main character. So like takes a look around, and on the left there's I, on the right there's going, on the right two positions to the right there's 2, 3 movies, 4 and then it's going's turn, going, like this. So if every token or every term takes a turn to take a look around what's around it, using attention, then the model will be able to tell the context, because what we are after is after all understanding the context of the given text, right? So this is what's going to happen when you run a transformer. So a little bit more mathematically speaking, the core of self-attention is something called the QKV operation, or I think it's called scale dot product. But I don't think anybody uses that term anymore. Nor I don't think anybody uses QKV operation anymore either. But anyway, in order to run self-attention, you need 3 components: Q, K, and V. And the equation is pretty simple, actually. There's something called Q matrix, and there's K matrix, and then the V matrix. This is query matrix. This is query matrix. This is key matrix, and this is the value matrix. And you can see that the Q times K transpose divided by some constant value. We're going to talk about that. And then you normalize it by the softmax function. Then you multiply it to the V. So that's what's happening. That's what's happening here. So softmax QK transpose divided by D is this matrix. And then there's V matrix. Actually, this is all like, they are already word embedding. So this is I embedding, like embedding, going embedding. So this, if you think about this as a 256-dimensional word embeddings, then this is 6 by 256. So this is matrix. This is 6 by 6 matrix, right? So what's happening here is that in the first row, I is the main character. I is the protagonist. So this is the attention given to other tokens by I. So this is happening here. So I thinks of itself as a 0.5 attention worthy. So, and then like I thinks like gets a 0.1 attention. Going gets 0 attention. 2 gets 20%. Movies get 20%. End gets 0%. So I thinks that itself is very most important. So all in all, if you sum them up, this will be 1.0, as attention should be. Second time, it's like, so this is I's perspective. This is like's perspective. Like thinks that I gets 20% attention, and itself gets 60%, all the other gets 0, and movie gets 20%. So to sum up, this is again 1.0 to as attention should be. So you get what I'm saying, right? Then it's going to be it's going's perspective, it's two's perspective, movie perspective, and perspective, right? And obviously, this side is also I, like yada yada yada, right? So once you have this attention matrix, this is attention matrix 6x6. You multiply it. You do a matrix multiplication with the value embeddings, and you see that what's happening here is you do a dot product. Or inner product actually. So you take this and this, you do an inner product, and you get this, right? And then you take this and this, you do an inner product, you get this, right? So if you look at this here, I becoming this, like becoming this, you can see that I is only now, well, before it was 100%, it was 100% I, but now it's 50% I with other things mixed in. So it's 10% like, 20% two, 20% movies. So no longer is this pure I, but now it's kind of like, tainted, or to be more precise, now we inject context into it. And same thing happens with this. So that was before 100% like, but now it's only 60% like, and now it's 20% I and 20% movies come in to inject context, to incorporate context. And same thing happens here and here and here. Well, so this is the end. This is the outcome of the QKV matrix, the QKV operation. Question: do we fix the first and second row intention? Are we two vectors still in the same meaning, or does? Actually, that's a very good question. We'll get to that. So that's why we need position encoding. But to answer the question to Hyunmin, if you swap this part and this part, then this part gets swapped, but the contents doesn't change. So we'll talk about that. What form is the output? This is still a word vector. So I said this is 6x6, 6 by 256. If you multiply this will be 2 by 256. So this guy and this guy is the same. So it's still a word embedding. So we think on attention value reflects structural information of sequences. Structural information, not purely structural, semantic as well. You'll see that it also incorporates semantic information. What this incorporates is up to the task that we enforce on it, because this is going to be trained by backprop starting from the loss function. So whatever loss function you give, this will satisfy that loss function, or actually this will work in a way to minimize that loss function. So what kind of information is encoded here, whether it's structural, semantic, pragmatic, discourse, is up to the task. What's the benefit of including the context in the meaning? If you don't understand context, you're not going to understand anything, actually, because everything is about context in language. Unless actually, no. Even when you want to determine, the part of speeches of each word, like this is pronoun, this is verb, this is actually, I'm not sure what you call this. This is proposition. This is preposition. This is a noun. I guess there's something else, something other than some name for this. Anyway, so when you want to determine part of speeches, you still need to understand context, because sometimes you don't know whether people mean this thing or that thing. It's going to become linguistic when we dive into it. So let's not do that. Context is variable. Context is variable. Yes. So the only way to understand context is actually to use all your five senses: your eyes, your ears, your nose, and that's what we call context. But in language, in language or in NLP, context means information that you can collect from text, and it's what kind of things we want to talk about, or what the situation is. Anyway, thanks. So if the output is equal to existing word vector, is a feature. You'll now, actually, I think it's too early to talk about that. They can be used as a feature, or they can be used as the output. It's actually, if you remember that I talked about in RNN, in RNN. I like going to yada 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 in RNN. This becomes a word embedding or memory vector, or you can think of this as a word embedding as well, because each hidden vector or each memory vector represents the words given so far. You can think of this as this guy, this as this guy, this as this guy. It's just that we're no longer using for loop to encode words. We're using attention to encode words or to understand context. All right, I'm going to move on then. So, graphically speaking, what's happening here is, let's assume that you're given two words, thinking machines. And well, this looks like a 4-dimensional vector, but actually in the original transformer paper, I think the original embedding was 64 dimensions or something, but we'll get to that later. Anyway, so in here, it looks like a 4-dimensional vector and 4-dimensional word embedding. And there's QKV. So I said that QKV attention requires Q matrix, K matrix, V matrix, but so there's Q, the query, the key, and the value. So query, so there's query for each word. So there's Q1, Q2, key for each word, K1, K2, V for V1, V2. How you get this is there's a matrix called WQ, WKW. So these are the learnable parameters. When you multiply this guy with this guy, then you get this guy. When you multiply this guy with this guy, then you get this guy. So WQ serves as a query generator. WK serves as a key generator. WV serves as a value generator. So you multiply the words to each here, and you get this guy, this guy, this guy. You multiply this here, 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 you get this guy, this guy, this guy. So let's say that you already did that. So let's say that you have all the Q1, Q2, K1, K2, V1, V2. So what's happening here is now it's the thinking's turn. Every term, every token gets a turn, right? So it's thinking's turn. So when I say it's thinking's turn, this is the guy that looks around, that throws the question or query. So this guy is thinking. It's the thinking query. We use Q1 when it's thinking's turn to, or when it's the thinking's perspective, right? So we use Q1, and then we multiply Q1 with K1, or we do an inner product with Q1 and K1. So inner product between the two, you get 112 points. You would do a Q1 with K2 because Q1 is fixed because it's thinking's turn. So Q1 is fixed. So you get this guy and this guy. So you get 112 points and 96 points. So this is kind of like in the attention before you normalize, you get a real value between negative infinity to the positive infinity, right? And then you normalize with softmax. So it's very similar to that. You get 112 points and 96 points, meaning that Q1 thinks of thinking thinks of itself as this point, and thinking thinks of machines as 96 points, something like that. It's kind of like a compatibility or affinity score. And before you get into the softmax business, you first normalize a little bit. So you divide this value by 8. And the reason that you divide this value with 8 is because you see square root of dk. So dk is the size of the key value. Dk is the size of the key value. And it looks like 3, but actually I said that in the original transformer, the size of all these was 64. So you do a square root of 64, then you get 8. You get 8. And then you divide 112 by 8, you get 14. You divide, so you get 14. You divide 96 by 8, you get 12. So it's 12 and 14 and 12. Then you do a softmax. Softmax between this. So it's a 2-dimensional vector. You put a softmax on top of it, you get 88%, 12%. So divide by 8. This part is to normalize, or you want to scale. You want to properly scale the value depending on the size of the vector, size of the key vector. For example, if you put if you use a key vector that is really, really big, like 10,000 dimensional key vector, then this value will be too large. So you don't want that. You want the scores to be somehow normalized depending on the size of the key vector. So that's why you normalize by the square root of the key vector size. So that's that. And so this is softmax, and then you do this. So you do this. So what you see here is basically these are the attention scores given by thinking, and then you need to do this again when the machine's turn. It is machine's turn to do the attention calculation. So in that turn, you use Q2, do an inner product, Q2, do an inner product, and then you do the same thing here, and then you get a softmax, and then you get machine's perspective of attention. Right. So what's happening here is, well, we are still sticking to the thinking's perspective. Once you have the attention scores, you multiply this with the value vectors. So far you've only used Q and K1, Q and K2, and then you got here, right? Now it's time to use V1 and V2, the values, and you can see that V1, this is pretty clear, but this is a little bit opaque. This is like kind of like half transparent, and the reason that this half transparent is because we only use 12% of. This is 12% of V1, V2, 88% of V1. So you multiply them, and then you get Z1 and Z2. Actually, sorry, no. You multiply 88% V1, so you multiply this. Let me actually, this 0.88 times V1 plus 0.12 times V2, and then you get Z1 right here. Okay. So it's Z1 is the sum of these two, assuming that this is already 12%, this is already like 88%, then you sum them up, then you get Z1. So, oops. Right here. Question, even if the score is very large or not, softmax would still make it to some sort of, right? Yeah, that is true. But you just don't want these values to go out of proportion. Basically, it's just one operation. So why not? Just to make things manageable, right? And so we get Z1 from the thinking's turn. We do the exact same thing with machine's turn, and then we get Z2. Okay, the only difference is, in thinking's turn, we use Q1. In machine's turn, we use Q2. So far, the way I described it seems like we are running a for loop, because I said it's thinking's turn, we get Z1. Then it's machine's turn, then again, we get Z2. It means, so it kind of sounds like we're running a for loop over the input tokens, like once, twice, 3 times, 4 times, 5 times, and then each time we're getting Z1, Z2, Z3, Z4, Z5. So that was not the original intention, because the original intention of the transformer paper was, we didn't want to use for loop. We just wanted to use attention, not for loop, to speed things up, right? But so far, the way I described it seems like make it sound like we are running a for loop. So the truth is that we are actually not running a for loop, because we do everything in batch, in batch or in matrix form. So we don't use the first word, the machine. Sorry, let's put it here. This is thinking. This is machine, right? So instead of taking turns to get Q1 and Q2, taking turns to get K1 and K2, V1 and V2, we don't do that. We actually use that. We stack them as a matrix. So it's now 2 by 4, and this is 4 by 3. Then we get 2 by 3, and 2 by 4, 4 by 3. We get 2 by 3. So we just do it in one go. We get all the Qs in one go, all the Ks, all the Vs, because we use a matrix multiplication instead of taking turns. And so once you have this, once you have Q, K, Vs, so Q1, Q2, K1, K2, V1, V2, once we have this, then we can directly go into the current QKV operation, where we put Q, K transpose, you multiply them, then what do you get? It's 2, 3, 3, 2, then you get 2 by 2, right? Because there are two words, so you have 2 by 2 attention matrix. You divide them by square root of dk, then you get softmax, then you do a multiplication with 2 by 3, the value matrix, and then you finally get 2x3 Z matrix. So everything is in one go. You don't get Z1, then you get Z2. You just do it you do a matrix multiplication to get Z1 and Z2 at the same time. So you are no longer using for loop. You're using purely matrix multiplications and additions to get the contextualized vectors, word embeddings. All right, so far so clear? All right, so question. Why is this why they say the transform architecture is scalable in terms of size and therefore allows very large models? Partly yes, that is partly true. Another thing is so when you look at this this way, it seems like it's going to be faster than RNN because we're not running a for loop, but that is not the only reason that we call transformer models scalable. Because RNNs will not, if you stack like, I don't know, like tens of layers or hundreds of layers of RNN, and you okay, for example, let's assume that you have somehow managed the speed side of RNN. Like it's no longer like, you don't take up as long time as before, somehow, like magically. And you stack like hundreds of RNN layers. It's still not going to work as well as transformer because RNN has a strong inductive bias. It's by design. It's designed to handle only sequences, but transformer is not designed to handle anything. I've said this in the past, right? Transformer doesn't have any inductive bias. It's by design to handle anything. It's not designed to handle images. It's not designed to handle sequences, and it's not designed to handle graphs. It's not designed to handle 3Ds. It's not designed to handle anything. It has no bias. So that is why I would say is scalable. But as Wonjun said, computation side also makes it very scalable as well. So it's like a mix of things. Okay, so all right, so next one, yeah. So now you understand what's going on here, right? So if you look at this and this, now you understand what's going on. You get the entire attention matrix in one go by doing this operation, by doing this, and then you multiply this part with this part. So this is matrix, you get the final matrix. So everything is in one go. Question, but the output sequence generation is sequential, right? We haven't gotten there yet. We haven't talked about the decoding side. So we'll talk about that later. This is encoding side. Or actually, this is just attention. We haven't talked about anything about the sequence to sequence or encoder decoder at all. We just talked about what self-attention is. What is QKV operation? That's all we talked about. All right, I think there are no more questions. Is there? All right, so I think next one is quiz. So that's why I kept asking. So read this. And so you are given 5 input tokens of 256 dimensions. So again, give me your answers in private messages. Don't post it. Don't post it publicly. So you are given 5 input tokens of 12. So 5 input tokens, 1, 2, 3, 4, 5, each being 256, right? Each being 256. And you want to set the key vector, value vectors to be of size 64, 64, 128 dimensions. Which of the following is false? There could be multiple answers, actually. I'm going to give you guys 5 minutes. Okay, so the answer is everything is wrong. But I was going to give points to people who at least gave me 4 answers, like 1, 2, 3, 4, 2, 3, 4, 5, 1, 2, 3, 5, whatever. So for people who gave me 4 answers out, 4 choices or 4 numbers out of 5, they would get a 0.1. But the answer is everything is wrong. I would say this would be the hardest because you need to kind of understand how, you need to actually understand how RNN processes and how transform processes encodes it. It's not, I've already told you everything. So basically, if you've listened very carefully, you should be able to tell that they are all wrong. But this would be the hardest. We've already done this in the previous quiz, so you should be able to do this. So the output vector is obviously the same as the value vector, because I've told you that this guy and this guy has the same size. So the output value is actually 5 by 128. QKV operation does work. It doesn't matter whether this and this and this, or it's the important thing is that you just need to, this and this, they need to be the same, because you need to do the an inner product between Q and K's. I've told you that you need to do an inner product between this guy and this guy, so they need to be of the same size. The rest is actually it's your choice, and you only need three learnable matrices when you're doing this. 3 learnable matrices, and when you count them, it's actually, when you count them, it'll be 256 by 64, 256 by 64, 256 by 128. Those 3 matrices, if you sum them up, it won't be this. It'll be way less than this. And you need to call softmax function not 5 times. I said that you do it in batch, so you only call softmax once over the entire attention matrix. It's done in batch. It's done in batch. You only call softmax function once. And the last one, actually, if you think about how you encode RNN with this vanilla RNN WH plus UX 10H, 5 times, because you have 5 words 5 times. Compared to that, transformer does way more matrix multiplications, because you do once, twice, 3 times, and then you do again this and then this to get this. So you do way more matrix multiplication. So this might have been the trickiest one. So I hope everybody understands. All right, so any question? All right, I guess there are no questions. Because you call softmax function 1 time on this matrix once. This all pertains to not having to do a for loop over each words. Everything is done in batch. You get Q's and K's and V's, and then you do matrix multiplication here, call the softmax function once, and then you multiply it with V. The projected back. No, we haven't talked about that. Maybe you're using your prior knowledge, but we haven't talked anything about projecting it back to the original, wherever. Not really. No, not really. It's just the way that we call it. Maybe internally maybe internally the way softmax function is implemented in NumPy or wherever, or PyTorch, maybe it does 1 line at a time. Actually, no, it won't be in 1 line at a time, because if you do it in 1 line at a time, it's still like for loop. But you just, on the surface, you call softmax, you write your code once, softmax on matrix, with axis 0 or 1 or whatever. All right, so we have a lot to cover, so I'm going to move on to multi-head attention now. All right, so multi-head attention is just having more than one attention maps. So you see what attention map 1. So this is map 1. Then there's map 2, and potentially there could be map 3, map 4, map 5, map 6, 7, 8, 9, 10. And I think GPT-3 uses how many maps? So at least like, I don't know, 128 maps or something. So if you have, oh, actually, I can this. So once you have more than one map, what is it good for? So it means that you'll have, this is Z1, this is Z2, Z3, but you'll have another set of Z1, Z2. Well, we can call this Z prime 1, Z prime 2, Z prime 3. So you will have multiple outputs because you have more than one attention maps, meaning that you have more than one output here, 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 here. So what is it good for? So before we get to the purpose of having more than one attention maps, the way we implement it is pretty simple. You just copy paste everything that you've learned so far. So you have attention at 1. We call attention head now. Attention head 1 and attention head 2. So you do QKV operation in each head in the same manner, as we talked about so far. So you get QKVs, but they are now Q0 0. So there's Q01. Actually, I guess Q01, Q02. Actually, we should start with 0. So Q00, Q01, K00, K01, V00, V01, something like this. And then you'll have another set of QKVs. So this will be Q10, Q11, K110, K11, so on and so forth. Okay, so you have just different sets of Qs and Ks and Vs in each head. So once you do that, then you can get, so you can assume that what's going to happen, right? You do a K transpose divided by the square root of DK softmax and then multiply it with V0, which means that in each head, you'll get Z's out of it, right? You'll get Z's out of it. So this is those Z's. In each head, you get Z's. So now 0, 1, 7 means it denotes the number, the head number. It no longer denotes the token number. It's the head number. So Z0, Z1, Z7. So with this one set of input, you get 8 outputs. So in the original transformer paper, they did use 8 heads. So we're sticking to that description here. So once you do that, you can. So every time you add one more head to your head sets in your attention heads, you don't want the output to, like keep multiplying. So because you need to actually, you need to pass this output to the next layer. So you can't have too many tokens or too many outputs as you increase the number of heads. You need to have the same output as the input, hopefully in the same dimension. And so this is where it comes to play. So once you assume that you have 8 heads, so you have Z1, Z0, Z1, Z2, Z3, Z4, 5, 6, 7. You'll assume that you have concatenated everything from your multi heads, basically. And you want to revert it back to this size meaning this guy. So the way you do it is simply you concatenate them, and then you multiply with another matrix, a learnable matrix, which is of the size what it should be. So this is 2, 3 times 8, so it's 2 by 24, right? So this should be 24 by 4 in order to put it back to 2 by 4. So this was 2 by 24. This is 24 by 4. Then you multiply it, you get obviously 2 by 4. And the reason that we put it back to 2 by 4 is we want to match it to the original input, which was also 2 by 4. Okay, so you can assume that as you increase the number of attention heads, this guy will be longer and longer and longer, meaning that this guy will also get longer and longer and longer. And this itself is a learnable matrix. So it means that as you increase the size of your heads, this will be really, really long, really long. And you don't want that to happen. So in the modern implementation, you don't actually do this anymore. You don't actually do this. You actually have a fixed upper bound. Like, for example, okay, I'm going to have my hidden dimension to be like 1024. Then you split it into 8 parts. So that each gets how many? Like 128, 128, 120, something like this. You no longer just ignorantly increase this concatenation size and the WO size. You actually have set an upper bound, then you split it into different by the number of multiple heads. But in this particular class, we are sticking to the original transformer. So that's why we stick to this a little bit inefficient method here. by concatenating the output and then having the same sized learnable matrix to get it back to the original size. Question is the reason the reason the QKV is different for each attention head is because the input X is the same, but each W is exactly very precise. You see that this is all 0, 0, 0, and this is all 1, 1, 1. If you use the same W's, it won't make sense of having multiple heads. Each head has its own learnable parameters. This 0 has this, 1 has this, so that they can learn different meaning. All right, so the overall architecture looks like this. So you have input, or you have something from the previous layer. So this is from the layer 0. So this is the input. You might think of this as an input from like previous layer because we're going to stack multiple layers of transform. Anyway, so this is 2 by 4, and you have 8 heads, 0, 1, 7. So you have 8 heads. Each head does the same thing, QKV operation. You concatenate them, and then you use WO to get it back to the original size, which is this guy, or this guy, same thing. Right. So why do we use multiple heads then? Well, isn't like one attention enough, like we did in the RNN? The answer is no, actually. So it is not enough. You see here, what's happening here is this is layer 5, meaning this starting from layer 0. So the original transformer paper, they use 6 layers of encoder and 6 layers of decoder. And this is the encoder side. So starting from 0, 1, 2, 3, all the way to 5. So this is the last layer. And you see there are 5 colors, meaning using 8 heads. So there are 1, 2, 3, 4, 5, 6, 7, 8, meaning 8 attention heads. Attention heads. Right. So this is the attention heads of the last layer. And particularly the second head is highlighted. Second head. So it's all like, orange-ish. So what's happening is it's a self-attention. So this is how the input is understood by the encoder, and it's its perspective. I said that everyone has its own perspective, right? They each take turns. So it's now its perspective and how it attends to other terms, other tokens. So it attends to all the different tokens, but the strongest attention is given to these two. And it's like the darkest, it's like the brightest, and now it's like these part is like transparent, it's more or less. So the reason that it is attending to these two tokens is probably because if you read this sentence, the animal didn't cross the street because it was too tired. So the identity of this pronoun it is the animal. So that is probably why the second attention head is used as a pronoun resolution module, or some people say anaphora resolution or core reference resolution. But basically, this second attention head plays a role where it connects the identity of the pronoun. So it goes to the animal. If you go to the next slide or next figure, we've turned on the third attention, and looking at the third attention, it is now attending to tired the strongest. And probably the reason is because this sentence is kind of like it's a conjunction. So there's the first sentence connected with because, and then the second sentence. In the second sentence, there's the subject and the predicate. It's tired. It is tired. So that is probably why the third attention is kind of probably like a predicate resolver. So the attention is given to the predicate. 한국말로 서술어죠, 서술어. So obviously the second attention and the third attention plays a different role. Looking at the attention distribution. One, it gives the attention to the animal. The second one then gives the attention to the tired. And then if you turn on everything, you see the attention distribution being all different, which is pretty amazing, actually. It means that if you use multiple attentions without telling each attention head to serve a specific purpose, it'll still find this purpose somehow to maximize the performance of the given task, or minimize the loss, basically. So it's kind of like the CNN filters. So if you employ like 64 different kernels, then some kernel will focus on red color, some kernel focus on diagonal lines, some kernel focus on horizontal line, some kernel focus on like oval shapes. Like each kernel serves different purposes, even though you didn't tell each kernel to serve a different purpose. It just finds its own purpose. Just like that, in here you employ 8 different heads, and each head somehow finds its own purpose. So you see that all these make a very much linguistic sense, and this is kind of semantic, or I guess this is semantic and structural, but more or less semantic, because you understand the meaning of it was the animal, and you understand the predicate of it was tired. So there was a question so far back, like whether the attention is encoding structural information or not, but I would say it's both structural and semantic. Question: can it be overfit if there is a large number of attention heads? How many attention heads do people usually use? Actually, if you use too many attention heads when you give very small amount of training sample or training data, then it'll probably, like, all the heads will serve similar purpose, right? Like here, they serve a very different purpose. But if you use like 100 heads when you have only like, I don't know, 1,000 training samples, then all heads will like more or less behave the same. So it will be not an overfit, but kind of like an overkill. And how many attention heads do we use these days? It depends on how large you want your transformer to be. As I said, GPT-3 uses like hundreds of different heads. I forgot the exact number. Is there a guarantee that each attention head will serve a different? No, there is no guarantee. That's why you need to put a lot of data into it. If you want the attention head, if you want to maximize the use or the efficiency of all the attention heads, you should probably use a lot of training samples. Otherwise, they're all going to serve a similar purpose. All right, moving on. So what is now we're so how much we only have like 30 minutes. I'm not sure if we can cover all this. So what is transformer? So transformer encoder. So finally we're getting to the transformers, the actual transformer of the paper. So the paper, as I said, was proposed to do a sequence to sequence based translation. So translation, you need encoder and decoder. And it's the same deal. You put the French in and you want the English out, just like the RNN example that we talked about. But instead of using RNN in the encoder and decoder, you use transformer in the encoder and decoder. And actually, to be more precise, 6 sets of transformers in the encoder and 6 transformers in the decoder side. So it's like it's a 6-layer encoder and 6-layer decoder, and each encoder looks exactly the same. And each decoder looks exactly the same. It's just that they use different learnable parameters. The architecture is exactly the same. You just copy paste all over. If you look at the encoder side first, we're going to get to the decoder later, but if you look at the encoder side first, each encoder block, each encoder layer or block looks like this. So you put input words in. So it's like 4-dimensional word vectors. You have self-attention, this is exactly the QKV operation we talked about, QKV operation. So once you do QKV operation, you'll have Z1, Z2, Z3. You'll have Z1, Z2, Z3. You assume that you use multi-head attention here, but you reverted back to the original. So what we talked about in the multi-head attention is you want the final output to be the same dimension as the input. So the input is 3 times 4, because there are 3 tokens, with each token being 4 dimensions. So it's 3 by 4. You want the output to be the same. It's 3 by 4. So you have, once you pass through the self-attention layer, you will get the same size output. And then you have a bunch of feed-forward layer, but the feed-forward layer actually works separately. So you have, actually now it looks different, but bear with me. We just use different examples from time to time. So now we have only 2 inputs, but it's the same. So you have self-attention here, output. In the feed-forward layer, what we do is we apply feed-forward, one small feed-forward neural network separately or independently to each Z's. You can't actually have a large feed-forward that that takes in, that processes all these at the same time, then it'll have to be dynamically sized depending on the size of your input, right? That doesn't make sense. So you have one feed-forward neural network that is applied to each token independently. Then you get the final output. Then that is passed to the next layer, next block here. So next block will actually get the same input as the first block, same input. I mean, the same input size, at least. The size will be the same. So see what's happening here, right? So you get an input, you do a QKV operation, you get the output, and then you apply feed-forward network separately, independently, then you get the output. Then you pass it to the next layer. Same thing happens. Self-attention, feed-forward, then pass it to the next. So to be even more precise, there is a little bit of tricks going on. So there's self-attention, feed-forward. We covered this. We covered this part and this part. But there is actually add and normalize in between. So add and normalize is actually add and normalize. So the add part is the residual connection. We talked about ResNet and the residual connections. The reason that we use residual connection is to actually make the optimization process easier, right? If you remember that. 다 기억나시죠? 제가 하는 얘기 지금. residual connection이 나온 이유는 이 최적화 과정을 쉽게 해주기 위해서였잖아요. 그러니까 이 차분만큼만 학습을 하면 된다, 각 레이어에서. 그러려면은 스킵 커넥션을 이어줘야 된다. 기억나시겠죠? So by having a residual connection, now we only need to learn the differences only. If you remember the motivation behind residual ResNet. So there's thinking machines going in. We have positional encoding, but we'll talk about this later. So you can ignore this for now. You just put thinking in, machine in, and then you have QKV operation. You don't add and normalize. So add, I talked about this. Add is basically you have residual connection. Normalize, we use layer normalization. Instead of using batch normalization, we use layer normalization. Batch norm had its own shortcomings, right? We talked about how it behaved differently in the training phase and the test phase, right? So we no longer use batch norm, we use layer norm in transformers. So add and normalize is add is residual connection, normalize is layer normalization. So you do this once you do a self-attention, you kind of like make it easier to train the block, and then you do a feed forward, and then again you do add and normalize. So you have two add and normalize layers here. Then you put it to give it to the next layer. Question. In encoder sequence of blocks case, the parameter of each FFNN is different. Is obviously it's different. Each block has its own set of parameters. So the QKV operation here and QKV operation here, QKV operation here, they all use different WKs, WQs, WDs. Feed forward here, feed forward here, feed forward here. They all use different feed forwards. I said that they are the same. We use one small feed forward network and apply it independently. So they're all the same thing. This guy and this guy is the same thing. You just apply it multiple times different Z's independently. All right, so moving on then. So the final diagram would look like this. You have thinking machines going in, and then you see a bit of a color change here. The color change is due to the positional encoding. We'll talk about that later. So color change, and then you have self-attention. Then X1 and X2 will become Z1 and Z2. And then you add and normalize. So this part is the residual connection. You have adding part to Z, right? Then you do a layer norm after you do the addition. So layer norm, then you'll have a slightly different colored Z1 and Z2. You see the color change from here to here, right? And then you put it through a feed forward, do the same thing, and then you get the final output here and here, and then you put it, and then that becomes the input to the next layer. Intuition by layer norm is just, you want to, if you remember batch norm, if you remember the batch norm, there was a cube, and then batch norm was normalizing across this dimension. Layer norm is normalizing across different dimensions. So batch norm, you want to get the statistics of the batch. In layer norm, you don't care about the statistics of the batch or the size of the mini batch. You actually care about the size of the hidden dimension. But yeah, we don't have time to get into the intuition behind it. You can go back to the CNN class and then take a look at the video or the slides. Right, so now finally we're going to positional encoding. So far we've seen this a couple times, but I skipped explaining it. So now we go to positional encoding. So if you look at this in the beginning of the class, someone asked a very good question. What happens if we swap this guy and this guy, right? The answer was that then you'll get this guy here and this layer here, but the contents will not change because if also this will go. So if you swap this, if you swap the order of the tokens, like I going to whatever, instead of I like going whatever, right? When you go this way, then this and this will change size. This and this will change size. This and this will change size, change places, and that's it. That's it. But the values here will not change. If you think about the QKV operation, the values will not change at all. Values will not change at all, and that's a problem. That's a problem because you, for example, if you compare a sentence between you are a boy and are you a boy, the order has changed, but not just that, the semantics has changed because you're a boy is a statement. Are you a boy is a question, right? Yes, exactly. It's a permutation invariant. Yes, precisely. So by changing the order of the word, the meaning of the text or the context should change. But if you look at this, the context or the meaning of the words don't change because there is no concept of order. Everything is permutation invariant. So that means that actually self-attention or the QKV operation is not a sequence encoder. It's a set encoder because it doesn't care about the order of the tokens in the set or in the sequence. So it's a set encoder. So that is why I keep saying that transformer or the QKV operation specifically has no bias. It has no bias. So you can think of an image like there's I. This is pretty thick. There's I like going to movies and everything is connected. Like, is this complete? Yeah, I think this is complete. So everything is connected because, which means that this guy will take a look at all the other. This guy will take a look at all the other tokens, and this guy will take a look at all the other tokens. This guy will take a look at all the other tokens. So basically, each element in the set takes a look at everything else, and there is no order involved. So it's a set encoder. It's basically it's a fully connected graph. So you have a set of elements, and the elements, they're all completely connected. It's a fully connected graph. But the strength or the weight of the connection or the edge, the vertex and the edge in the graph, the strength of the edge or the weight of the edge is dynamically decided by the attention process. Whether this should be 0.1, 0.2, 0.5, 0.6, it's all determined dynamically, but at least everything is fully connected. So that is why it has no concept of order. Everything is fully connected. That is why it has no bias, and everything is determined data-driven, completely data-driven, because you don't decide the strength of the edges. It's the loss function and the given data set that determines the strength of the edges. So that is why it has no bias, and that is why it's way more scalable than CNN, which only cares about immediate neighbor pixels, or RNN, which only cares about immediate next to. So CNN, actually, this is going a little bit overboard. CNN assumes a graph that looks like this. This is the graph that CNN assumes, and RNN assumes this graph. It's a chain. So CNN has a bias, inductive bias, that assumes that your input set forms a graph like this, And RNN assumes that your input set forms a graph like this. But your transformer doesn't have any assumption. It's just fully connected. Everything is fully connected. So we're missing this. Like it's missing a lot of connections. Here it's missing this, like a lot of, but this is not missing anything. Everything is fully connected. So that is why it has zero bias. That is why it's the most scalable, because it has no assumption. You can just pour it. Actually, you need as many samples or as much training data as possible to make these edges, the strength of the edges, as accurate as possible. In practices, if you input an entire novel in, is it getting the context for each words from the entire novel, or it has certain? It is actually, you can't put the entire novel because of the hardware limits. You see that, we haven't talked about this, but you see that in order to get a fully connected graph, you need this matrix where each side has the same number as the input tokens. So it's, if you have 6 tokens in, you need 6 by 6 matrix to get the fully connected graph. If you have entire novel put in, that would be like 1 million tokens, for example. Then this will be 1 million by 1 million matrix. And this doesn't fit anywhere. You can fit 1 million by 1 million matrix in a VRAM. So that doesn't work. That is why modern GPTs, they have a certain limitation to their context window. I think the largest GPT-4 context window is 32,000. So 32,000 is how far we have come as a humanity. There are others that claims that their context window is limitless or like infinite, but that means that they're not actually assuming fully connected graph. They're like kind of approximating by using a sparse attention or something, or they're using like recurrence plus transformer to encode it recurrently. Like they're using some kind of trick. But if you're talking about the pure QKV, you need quadratically increasing attention map, quadratically increasing by the number of tokens. If the convolution kernel is extremely large, does it approximate the transform graph? Sure, yeah, that would be correct, but the problem is that it's not dynamic. The convolution kernel, the kernel strength is fixed, but here, these attention maps are dynamically calculated based on the context. But in kernel, if you think about CNN kernels, their kernel strengths are fixed. So it's a little bit different. And that would be almost like having a fully connected graph. I mean, fully connected layer. So I'm not sure if that makes sense as a CNN anymore. All right, so far we talked about the permutation invariance and the true identity of QKV operation, which was set encoding. So we need some. So as I said, we want to prevent this kind of thing happening, right? So what we do is we need to inject the concept of order into the transformer. So that's where positional encoding comes in. So somehow you want to tell the model that this is in the first place, this is the second place, third place. But more importantly, what you want to do is, for example, let's erase all this. More importantly, what you want to do, let's assume that there is, I like going to, right, let's assume that this is not movies, but this was like. Just for the sake of the argument, I like going to like. That's our sentence. In that case, what happens if you don't have the order of the concept of order? That means that these attention here and attention here will be exactly the same, because they will be this like will go through the WK, WQ, WV. This like will go to WQ, WK, WV, right? And they'll all give the same QKVs. Given the same QKVs, their attention strength will be the same, which means their output will be the same. So if you have the same token inside your sentence without the concept of order, their output will be exactly the same. So there is no difference between the meaning of these words depending on their places in the sentence. And we want to prevent that from happening, right? So that is where this position encoding comes in. So not only do you want to give order concept into it, fundamentally what you want to do is you want to basically differentiate between words that have the same surface form but in different places, so that you will get different outputs. That is why we need position encoding. But on the surface, but more simply put, we just want to give the model that this is in the first place, second place, third place, fourth place, fifth place, so on and so forth. But fundamentally, what we want to do is we want to differentiate between different places. Right. So how do we do it? How do we set up the positional encoding? So there are certain rules that we want to satisfy. For example, if you want to tell the model the position of each token, it should output a unique encoding for each time step. So like first place will get its own position encoding. So you see that the position encoding has the same dimension as the input, right? If this is 4 dimension, this is 4 dimension. If this is 4, 4, 4, 4, right? So we have a vector, position vector, actually, not just a scalar value, but we have a position vector. So we should output a unique encoding or unique vector for each time step. And distance between any two time steps should be consistent across distances with different lengths. For example, like you have 1, 2, 3, 4, 5. Like I like going to movies, something, and then like 1, 2, 3, 4, 5, 6. Do you like going to movies? Something like that. Then you want the distance between this and this to be the same. Obviously, distance like they should all be the same. Actually, distance between they shouldn't be like distance between or the order the length. Yeah, I will say distance between like 2, 3, 2, 4, 2, 5, 2, 3, 2, 4, 2, 5 should be the same. It shouldn't change depending on the size of your input, right? And our model should generalize the longer sentences without any effort. So once you've trained your model on like input size up to 5. And on the test phase, you put 6 or 7 tokens in, it should still work. And actually, this is a very very respectable, like a very favorable concept, but it actually doesn't really work that well. Even with positional encoding, it doesn't work too well. So there's like a lot of tricks going on to make this happen, but we'll talk about that later. And it should be deterministic. Obviously, it should be deterministic. Like one should give the same position vector all the time. It shouldn't be like stochastic. So if you have all these like position requirements that you need to satisfy, you can think of some candidate position embeddings or position vectors. So one candidate is this, another candidate is this. So these are all scalar. So basically, the easiest thing you can do is 1, 2, 3, 4, 5, 6, 7. Or the second one is because if you look at this 1, 2, 3, 4, 5, 6, 7, then in the test phase, if your test sequence is a little bit longer than your training sequence, then you'll see suddenly a new position, 8. And there is no 8 in the training sample, 8 in the test sample. So which means that your model has never seen 8 before. So something might go wrong. So that's not good, right? So let's say that you want to normalize. So you want your maximum the upper bound to be 1. So this is your final embedding or final position embedding, regardless of the size of your input. So here 1, and this is also 1. Then you need to split this 1 into 7 evenly distributed values or 8 evenly distributed values, right? But now but the values now slightly changed. Like this was 0, 1, 4, but now it's 0, 1, 2. 2, 8, 2, 5, 4, 2, 7, 3, 5, 6, 5, 0. So again, these are the values that the model has not seen during training. So there's like always like some kind of trade-off between different conditions. So another thing that you could do is using binary values. So if once you're going like multi-dimensional, like you're using 4-dimension position encoding, right? Then why not just use all dimensions like this? So the first one gets 0, 0, 0, 0. The second one gets 0, 0, 0, 1. The third one gets 0, 0, 1, 0, 0, 0, 1, 1. So it's basically you have binary numbers. Binary numbers denoting this position of each position, basically. So you can go up to 15. So the problem with this is, I mean, this is pretty good. Like, this is pretty good. But the problem is, it's a waste of space because you're using only zeros and ones in each each dimension, you can only denote up to 15 with 4 dimensions. So 5 dimensions, you can denote up to 32. 6 dimensions, you can denote up to, what, 64. So there's like certain limitation to the efficiency side. But here you can see what's happening in each dimension, and that's what Google researchers came up focus on. So in the first dimension, you see it's changing very rapidly, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. In the second dimension, it's changing a little bit less frequently. So 0, 0, 1, 1, 0, 0, 1, 1, and now it's 0, 0, 0, 1, 1, 1, 1, and now it's 0, 1. So each dimension has different frequency. If you think of this as a signal, like this, and like this, and like this, and like this. So they have different signals. So this was the reason behind using the sinusoidal function. If anybody knows sinusoidal function already, this is the reasoning behind using sinusoidal function to represent positions. So this is they use 128-dimensional vector to denote the position embedding here. So this is 4, here is 128. And you can see that in the first dimension, you see, so yeah, positive one is blue, negative one is red. So, and this is a sinusoidal function. So it's just a sine function, basically. You see it's changing very rapidly. So it's like this. You see the colors like blue, red, red, blue, red, like it's very rapidly changing. But if you go to like later, the higher dimensions here, for example, now it's blue, red. Yeah, this is not a very good drawing. Anyway, you see that this is all blue. Now it's red. And now it's blue. So only 3 times. If you look at the error, there's like blue, red, blue. So it's like, yes, I think it's like this. So you can see what's happening here, right? So the first position gets this vector. Second position gets this vector. Third position gets this vector. Fourth, and the 50th position gets this vector. And you can see a lot of the remaining ones. They're all the same. It's mostly the first part that actually makes a difference between different positions. And it's not seen here, but actually in the sinusoidal position embedding, they use sine and cosine alternatingly. So actually here, this is sine function, this is cosine function, this is sine function, cosine function. So these two get the same frequency. These two get the same frequency. These two get the same frequency. But basically, the reasoning behind it is basically it's not so different from this. Not so different from this. So you see the equation here. So these days, people either use sinusoidal functions or they use actually learnable functions too. So they have, for example, let's assume that you're going to train a transformer that only accepts up to 128 tokens and nothing more. You can only accept up to 128 tokens. Then you just need to prepare 128 positional vectors and then train it. So sinusoidal function is not a trainable function. It's a fixed function based on this, according to this equation. But a trainable positional embedding uses trainable positions. So these become all trainable variables. Each position has its own trainable positions. And that's okay. It doesn't have to be like, it doesn't have to encode some concept of 1, 2, 3, because as I said, the only thing that we really care about is differentiating between different positions so that this doesn't happen. So they only need to differentiate between different positions. So you can use trainable vectors as well. Okay, so to wrap up, I don't think we have time to actually finish all the contents today. Maybe I need to use a little bit of the practice time this Thursday to wrap up. So RNN 1D conv, and so the way that we use the way that we encode sequences, there are 3 main philosophies. One is obviously using RNN. So you give 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 tokens in, you get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hidden layers, hidden vectors, hidden layers, or hidden vectors. And they all each represent each vector, each word. It's representation of each word. CNN, you can use 1D CNN. I talked about this in the CNN class. You can use 1D CNN to slide your one-dimensional kernel across the words and then get the embeddings. So if you assume that there's like paddings here, then the output vectors will be the same as the input vectors. So for example, if you stack two CNN layers, like one layer, two layer, then the output vector here will be the same. Well, I mean, it will depend on the number of kernels you use, but still, like you can have the same number of tokens or same number of vectors as input. Just like you have H1, H2, H10 here, each representing each word. Here you have here, each representing each token. And in Transformer, the same thing. Transformer, no matter how many layers you will have the same number of tokens, output token, as the number of input tokens. So each potentially representing each word. But compared to this really represent this really represent this, and this really represent, actually, this represents this and this represent this, and this represent this, right? CNN will actually, with two layers, this guy will represent like this, right? And this guy will represent this, something like that. So the receptive field will be this. This guy, for example, this could represent the entire thing because everything is fully connected. The attention is given to everything. And this guy could also be connected to everything, also everything. So no longer can we say that this guy is representative of this guy is representative. We can't no longer say that for sure. It's probably that, but we don't know what the attention strength would be. So maybe this guy would represent this. Who knows? So it's just, but the number of output tokens is still the same. Question, could I ask why sinusoidal function is better than binary encoding? Sinusoidal gives unique position encoding for each word. No, actually, the important thing is this is binary. This is real. This is real. This is real value. So you're not wasting any more dimensions. If you use binary, you can only go up to 15. But if you use continuous value using sinusoidal functions, cosine sine, you can go to 100, 200, 1,000, 100,000, whatever. So your upper bound is no longer how far you can go is no longer determined by the dimension of your position embedding. Before binary, your upper bound was determined by how many dimensions you use, but here no longer because you're using continuous real value. Hope that makes sense. Right, so far we talked about the difference between, or more or less similarity and difference between RNN and 1D convent transformer. So now it's time to go to sequence to sequence, but unfortunately we don't have enough time, so I guess we'll have to actually skip to put this into the next practice session. We have a lot to cover, actually. We have a lot to cover. Yeah, we've only come like 60% or 65% of the contents that we need to cover today. All right, so let's begin. So we have only 30 minutes to go. So sequence to sequence, and so we've covered, last time we covered self-attention, then transformer encoder, the position encoding, and then the last thing I talked about was encoding sequences. You can do it with either RNN or 1D CNN transformer. Doesn't really matter. It's the design is different. The fundamental design of these different encoders are different, but the output will, the input and output will be exactly the same because the number of tokens you put in, the same number of tokens will come out of both RNN, 1, 2, 3, 4, 5, 6, 10, 1, 2, 3, 4, 5, 6, 10, and then the same number of tokens will come out. So that was the end, the last thing we talked about. So now we'll go into sequence to sequence. So as I said in the previous session, the transformer paper, attention is all you need. That paper was proposed to perform translation. So there's obviously encoder and decoder. And so far we've only talked about encoder. Well, actually we talked about the single encoder, and then the rest of them was a copy paste, right? So now we can talk about a single decoder, and the rest will be obviously a copy paste again. So the single encoder looked exactly like this. So decoder is a little bit different. Okay, so I'm gonna have to. Okay, actually, I can't mute everybody because I am not the host. So please, if you've turned your mics on, please mute yourselves because I can hear you and everybody else can actually hear you. All right. So as I said, decoder is mostly the same, but mostly the same as the encoder, but there are two differences. So first of all, there are two attention components. So in the encoder, there was only one self-attention, then there was feed forward, and that was it. But now we have two attentions, attention 1 and attention 2. So there are two attentions, and even the first attention is called masked self-attention. So this is just self-attention, right? There is no masked here, but this is masked self-attention. So this is a little bit different. And then there's encoder decoder attention, and then we have feed forward, and then the rest is exactly the same. The rest is just copy paste for the same, copy pasting the same, decoder over and over again. So obviously this self-attention is used to understand the decoded tokens so far, because if you remember RNN, sequence to sequence RNN, there was, French words were going in, and then nothing coming out of here. We just take the last. It's not the attention based sequence. We're just talking about the plain sequence to sequence RNN model. The last hidden layer became the first hidden layer of the decoder, and in the decoder, the input was English, right? It was the English ground truth English tokens were coming in during training, right? And then so if this was like, let me see, if this was I am a boy something, then this would be, oops, wait, it says that I couldn't share my screen. Okay, let me just start. 지금은 보이시죠? 네네, 좋습니다. Actually, so this would be am a boy, and there's actually hidden start. There's a start, and then there's I, right? So this here is the ground. During training, we could put the ground truth into the decoder RNN, right? Decoder RNN, and then we would have for each time step predict the next step input, the next token, right? So that was how we trained it. And some people call this, teacher forcing, because we are actually, using the ground truth to true ground truth during training. So we're into the decoder, we're putting the actual ground truth. So some people call this teacher forcing. So just like that, in the transformer encoder decoder, in here goes French words, or actually thinking machines, and then in here goes the ground truth that the thing that we want to translate this into. So this will be the ground truth. So this mask self-attention will be used to understand the ground truth, or during test phase, understand the decoded tokens so far, the decoded tokens that this decoder decoded so far. So this is used for that. Encoder decoder attention is used to understand what has been given to the encoder. So you can see that something is coming out of here and here, right? So if you remember correctly, that we will be seeing two tokens coming out from here, because the number of tokens coming in and coming out of encoder is the same. So we'll see two contextualized embeddings, or contextualized vectors, word vectors coming out, and we will take this and somehow put it here and here, so that a decoder can understand what has been going on in the encoder using this encoder decoder attention. So here, this one, so on a high level, this is used to understand what has been decoded so far, or what has been generated so far. This is to understand, well, actually mix. This is to mix what has been generated so far, because you're getting the information from here and here at the same time. So this is to understand what has been mixed, what has been decoded so far, and what has been given to the encoder. So this is a mixing part, and then we have the feed-forward, and that's it. Oh, and obviously there's the positional encoding as well. I forgot to put that in. So this plus sign is the positional encoding. So let's see it one by one. So French, we are translating French words into English words. So it's French sentence. So we put French sentence to the encoder. So you know that this is the word embedding. This is the slightly modified word embedding because of the position embedding. So you see the color change here, and then we put that into the encoder, and decoder is ready to decode. So there's a bunch of decoder, like multiple layers of decoder, and then we have the final linear layer in the softmax to predict the exact token, right, at each timestamp. So you see the blue ones here. This is the output of the encoder. So we can see 3 contextualized embeddings, each for this word, this word, this word, right? So what happens is you see this encoder decoder attention. What this does is, as I said, this is mixing what has been decoded so far and mixing the decoded output and the encoder output, right? Encoder output and decoder input, or you can see it like that. So that this is the mixing part. So what happens here is you first take this and then turn this into K. Actually, we turn this into K and V, K and V, K and V. So why are they? This is obviously key 1, key 2, key 3, value 1, value 2, value 3. We first of all we convert them into keys and values first, and then we use them in the later stage. We'll see later. So this is key encoder decoder, V encoder decoder. So this is like 1, 2, 3 here, and 1, 2, 3 here, right? And obviously we need the start token, just like in the RNN sequence RNN. In the transformer in sequence to sequence, we still need the start token. So we put the start token in, and then what happens is that obviously you want the output to be I. So here and then here, we want the first output to be I. So because JSW Ichujin, actually I forgot to write the correct translation. The correct translation to this is I am a student, end symbol, right? So we want the first start to go and be translated or be predicted into I, and then the next one obviously we put I in and it should go into M, and then we put M in, should be M, and then student, then student, finally end of sentence, EOS. So the steps are exactly the same as the sequence to sequence RNN. So the input and output look exactly the same. So there's nothing too complex here, right? And then the last one is obviously the softmax layer. I won't go into detail. You just have so you put one token in, you have 1 token out, another token to another. So if you put 5 tokens in, then obviously there will be 5 tokens out. 1, 2, 3, 4, 5 tokens. Just like here's 1, 2, 3, there's 1, 2, 3. There will be 1, 2, 3, 4, 5. There's 1, 2, 3, 4, 5, obviously. And then we take one output, we take one contextual embedding or the word vector, and then put it into, that becomes, this is it. We put it into linear layer and then softmax layer so that we can predict the correct word in your vocabulary. So you do that for all 5 of these, take this into linear layer, softmax, linear layer, softmax, linear layer, linear softmax, right? So we can correctly predict I am a student, EOS. So if you remember, so let's just a quick recap. In the encoders, before we go into the encoder decoder attention, the mixing part, before we go into that, encoder's self-attention at the thinking's turn, every turn, every token had a turn, right? Even though the entire processing was done in batch, conceptually, I said that each token had a turn. So when it was a thinking's turn, the query thinking, we used the Q1. So we use thinking's query as the center of attention, and then we use K1, K2 to do an inner product. Inner product here, and then we get the score, normalized score, and then we multiply this to this, this to this, and then sum them up, and then we get Z1, right? So in the encoder decoder attention, the mixing part, let's assume that we are predicting the I token, the first token. So we have only start as input. So it's the start's turn. Actually, there is no other turn because we only have start and. So it's the start's turn, and then we want to generate query. So it's start's turn. So it's we use the query of the center of the main character, and the main character is start. So we have start, because inside here, actually I forgot to draw it. Inside here in the encoder, decoder, attention, this is an attention part. So we already have K's and V's here. We already have K's and V's, which were coming from here, right? We already, oops, yeah, this, yeah, anyway, the details are. So yeah, we already took them and then converted them to keys and values. So we already have keys and values ready. We only need the queries, and the queries come from this part, this start token, because it's now this turn, the start's turn. So we have query value. We use query using start, and then we generate keys and values with all three outputs. So we already have them, and then we calculate scores based on queries and keys. So what happens is we take the query. So there will be query here. We take start query, and then we do an inner product with this guy and all these three. Inner product. Then we'll have some scores, and then we will normalize them using, dividing by the square root of the DK, and then applying the softmax. We will have a corresponding normalized attention distribution. So for example, this could be 0.67, this could be 0.21, this could be what, 0.02? Yeah, sum to 1. So this could, yeah, something like that. So we have that, and then we have, based on these scores, 67%, 21%, 2%, we multiply that to the value vectors, and then we sum them up, and then we will have Z coming out. So that's what happens in the encoder decoder, the mixing part. We mix the Q and the K's and V's inside here, and then we get a Z out. So that's exactly what's happening. Then using this Z, we will use it to predict the output I. Right? So far so clear. In the M's turn, so we first had the start's turn, right? So let's assume that it's the it's I's turn. Actually, it's the I's turn now, because we've already did this. So we are now going to this, and it's I's turn. So we generate query using I. Do the same thing. I's query, inner product with this, and then we'll have some attention distribution, like some attention distribution here. We multiply that with the values, and then we sum them up, and then we'll have the corresponding Z here, and we'll use that Z to predict M. Then moving on, we keep doing that until now it's the student's turn, the end of the last one. So it's the student's turn. We convert student token this into Q, and then we do the same thing, inner product, normalize with softmax, and then multiply that with value, and then we get Z out, and then we use that Z to predict end of sentence. So it's exactly like this. So it's the encoder decoder attention. It's just unlike the self-attention, where Q and K's and V's all come from the input, in the encoder decoder attention, the queries come from the decoder input, and the keys and values come from the output of the encoders. So hopefully that's clear. Let me just check the chat, if there is any chat. Okay, so there's a chat. Okay, hopefully everybody's following along. So exactly the same. We run into the same problem as when we were running the RNN sequence model. During training and testing, things are different. During training, we had all the we knew all the GT, the ground truth, so we could actually use them to train it. But in the testing phase, we need the decoder to predict its output and then use that as its own input. Predict its the next token, use that as the next input. Predict the next token, use that as the next input. So on and so forth, just like in the RNN. So that much is the same. So let's write it down. In the RNN and transformer, transformer. During training and testing, during testing, we still have to, both have to generate, so regressively generate one token at a time, during testing. So this much is the same here. In the RNN and transformer, this much is the same. But testing is different. In RNN, training during training. Testing is the same. We need to generate one token at a time. But training, RNN during training, we had to put one token to the decoder at a time, because RNN is inherently just it has a for loop inside. But transformer, the purpose of transformers was to do everything in a single go. Just like in the encoder, we put all the inputs in the transformer in encoder, all at the same time. We don't process one token at a time. We put all tokens as a batch, and then we put it in, and then we get all tokens out, right? Same deal in the transformer decoder as well. During training, only during training, we could put all the GT tokens in, and then we could get all the GT tokens, GT1, 2, 3, 4, 5 out, and then use softmax all independently, and then generate I am a student, end of sentence, all at the same time. So we put, before here, I again explained such that each token was going in one at a time, and then each token taking one turn at a time, being the query, and then doing the inner product here. But that's not actually the case. We put 5 tokens all at the same time. All 5 tokens at the same time. They all become queries all at the same time, and then we do an inner product all at the same time. Just like in the how we did this here in the self-attention, we did it in a matrix form, right? We processed everything in a batch using matrix multiplication. Same deal here in the encoder decoder attention. Same deal here. We put all of them in and then do a matrix multiplication to get everything, the contextualized vectors all at the same time. So at least during training, transformer can take everything all at the same time. Unlike RNN, which has to take one token at a time. But during testing, they have the same thing. They have to generate one token at a time. Hopefully that makes it clear. Right. So that's what's happening here. Yeah, not really. So not one query, not one query at a time. We put everything in at the same time. So during training, we do know the GT English sentence, the ground truth English sentence, but during testing, we don't know ground truth English sentence. So we talked about this so far. So we generate one token at a time, just like in the RNN case, one token at a time. So in here, what would happen is this will be your prediction. I'm talking about the testing phase. This will be your prediction. You put your prediction in as I, and then you'll get something. You get some output, which will be hopefully M. Then you can take M, put it here, M. Then you have the same output. Some output which hopefully will be a student. Then here student, you put student in, something like that. Just like one token at a time. Right. So in the one token using autoregressive generation. So here, this comes pretty important. So because during training, we put everything in at the same time, but at testing we can't do that. So there's a gap between how we train the transformer and how we use the transformer in the test phase. So let's assume that we are currently in the process of given IM so far, we are trying to predict the A token, next token. So this is a testing phase. This is test phase. During test phase, we have this put into the encoder. We have this. This is given to us, right? We have the French words given in, and then so far we have somehow luckily predicted IM. So we put IM into the decoder, and now it's turn to predict A using the M's output here, right? So this is the situation. What's happening here is that in the encoder attention, we have self-attention going on. So JSui Etudiant, for example, the encoder attention from Sui. So Sui is now the query in the self-attention, and Sui can attend to all the other tokens. It's self-included. It can attend to itself, it can attend to J, it can attend to etudiant. So it's all fine in self-attention. But in the decoder, we have so far put I and M into the decoder. And also let's assume that M is the query now. So M is the query. And now M, if we're following the self-attention, so we're, let's be really clear what I'm trying to talk about here. So what I'm trying to talk about here is that if you look at the decoder, there was masked self-attention, and there was encoder, decoder attention, and then there was feed forward, right? I'm just ignoring the add and normalize part. So we've talked about this part. We don't need to talk about this. Everybody knows this. So we talked about this part so far. I'm now talking about this part and why we need some kind of additional trick in addition to just pure self-attention. So what's happening here? This is the situation. So we have I and M put in, and M is the query. So M is the query. And when M is the query, what's happening here is that we want to do a self-attention. So if we're doing the same self-attention as the encoder, then what would happen is M being the query, it will attend to itself, I, A, and student all at the same time, because this will be actually given in the training phase. This will be given at the same time. So when we're training it, we can, if we wanted to, we can use M as a query and attend to I, itself, A, and student. We could do that. But the reason that we should not do that is because we should not do this is because we are actually, if we do this, then we are actually using the information from the future. When during the test, in the test phase, we won't be having these GTs. We can't have, so the GTs, let me put it here. A, student, and actually there is the hidden start token. So student, right? So in the test, in the training phase, we will see everything at the same time. So the mass self-attention can also see everything at the same time, but that's just the training phase. In the test phase, for example, if we have somehow got lucky enough to get to here, we don't have this in our input. We don't know what's going to happen in the future. So this is the future. This is the future, right? So we don't know this. So if we don't know this, we should not attend to this. If we do, then we will be actually using the future information. And when using the future information, it would be super easy to, so there will be 3 outputs. This is the start output, I output, M output. Using the M output, it would be super easy to predict the next token, which is A, because we already have access to A. If we allow M to attend to A, then using this to predict the next token A would be very trivial. So we shouldn't do that. We should not actually let all the tokens look into the future. We should prevent that from happening. So what we want to do is we want to somehow make this happen. So only M as a query can only attend to itself and the previous token. Same manner, when it's I's turn, I should be allowed to only look at itself and the start token actually. And when it's the A's turn, we should allow A to only look at this itself and the previous tokens. So this is where the gap between the training and the test comes in, because during training, we put everything in and then train at the same time. But at test, we can't do that. So during training, we should take that into account, what's going to happen in the test phase, and then train as accordingly. So that's what's happening here. So we want this to happen. So if you look at the encoder side, everything is attending to itself in the future, itself in the future, itself as well. But in the decoder, well, actually, if you look at the arrows, nothing really goes to the future at all. There's no future, no arrow going to the future. It only goes to itself or the past. So I can only attend to itself, M is self and I, A itself and M and I, student itself and A, M and I. So we need to enforce this kind of behavior in the masked self-attention. So that's why we call masked self-attention, actually, not just self-attention. So how we enforce this kind of behavior is using mask, because that's why we call it masked self-attention, because we use mask. So where do we use the mask? We use the mask on this attention matrix. Well, actually, this is not attention matrix. This is like a score matrix, because so previously the attention matrix was like this, softmax. So we have QK, we have QK transpose divided by the square root of the DK, and then we apply softmax, and then this will all be sum to 1. So the sum to 1 will be enforced. But in the masked self-attention, what happens is you take this, the pre-softmaxed attention map, multiply that with this lower triangular mask, and you can see that the lower triangle is 1, and the upper triangle is filled with negative infinity. So when you multiply this and this, what happens is you'll get something like this. This is what we want, right? This is when it's I's turn. We want I to only attend to itself, never into the future. When it's like's turn, it will attend to itself and the past. When it's going's turn, it will attend to itself and the past, but never into the future. So no, like future attention is not allowed in the masked self-attention, and the output will be exactly like this. So in order to obtain this kind of attention map, you need to multiply this lower triangular matrix to pre-softmax attention map, and then so if you're wondering why we're doing this, if you simply put, you could ask why not just for example, why not do this first and then multiply this matrix with not this but zero filled matrix. If you do this, then this won't be normalized. This won't be sum to 1. So this will actually be less than 1, because you're enforcing this 0, 1 thing after the softmax. So the sum to 1 will not be preserved. So in order to preserve the sum to 1 principle, you need to do something before you put the attention in, before you apply the attention part. And the reason that we use negative infinity is because if you just put 0 here and then multiply it to this part and then do a softmax, then this part will not be 0. So you will not see zeros here. It's supposed to be some very small value, like 0.01, 0.01, 0.0, because 0 will not give you a softmax output of 0%. Only when you put negative infinity, that will ensure that your softmax output will be 0%. So you can try it out if you're interested. See what happens when you put 0 here. So yeah, we are hoping that we could get something like this. Let me see if there's any questions so far. Okay, so yeah, Masa. So in training phase, we generate all decoded output tokens at once and then multiply the triangular matrix. So yes, exactly. So yeah, that is very true. I'm a bit confused how we don't use future, but we generate all decode output tokens. This is how we do it, because we put, let me go back to the slide. Yeah, even though we put all the GT tokens into the decoder and then make the prediction all at the same time in one go, so we want to do this during training, but we don't want this to somehow ruin the test performance. So the trick that we use to prevent that from happening, ruining the test performance, is the masked self-attention. Because even though we put all the GT tokens in at the same time, as long as we enforce the tokens not to attend to the future, then it will preserve the same behavior that we want to see during test phase. So that is where masked self-attention comes in, and it's the very important part. If without just if you just allow self-attention, then as I said, predicting the next token will be very trivial, because M knows that the next token is A knows the next token is student, so we don't want that happening. Let me see. Chat. Good. Okay, you got it. All right, so the last one is a quiz. So I'll give you guys 5 minutes. Actually, it's already 11. So hopefully we can wrap things up in 5 minutes. So which of the following is true? So there are 5 potential answers, and this again is the same multi answer. There could be the same. I'm sorry, same as the quiz one. There can be multiple true answers. So choose whatever you want. I'll give you guys, yeah, well, maybe 4 minutes now. So the answer is actually, well, we can take a look at it one by one. So mass self-attention must be used in all layers of transform decoder. This is true, obviously, because if not, then even if we prevent future information leaking from the first layer, if we do not use mass self-attention in the second layer, then the future leaking will happen anyway. So you have to use mass self-attention in all the layers to prevent that kind of future information leaking happening. So this is true. We can use one layer vanilla RNN encoder, one layer transformer decoder to form a sequence model. This is also true. Doesn't matter what kind of encoder decoder you use. It's up to your design choice. I'm not sure if there's no reason to do this anyway, but you can do it if you wanted to. Or you can do it the other way. Actually, you could put transformer encoder and then use RNN decoder. Doesn't really matter as long as you can. So if you use RNN encoder, what would look like is there's an RNN encoder here, and then you'll have input tokens. Let's say that there are 3 input tokens, and there will be 3 output tokens, right? 3 output tokens, and then they will be this will be converted to Ks and Vs using WK and WQ, WV. And then there will be transformer, and the transformer it'll be the same. You know, there's input here, and then there's output here, and then these KVs will be used in the encoder decoder attention. There's mask self-attention. It's exactly the same. So why not? In the multi-head attention, the number of heads must be an even number. No, it doesn't have to be even number. It could be any number you want, but people just use even numbers. And so this is true. This is true. This is not. The negative infinity mask must be lower triangular to prevent information leak from the future tokens. Actually, this might have been the tricky one. This is not true. This is not true. Your mask can actually look like this. This will also, so maybe in a red color. This will also prevent future leaking from happening, you know. But then they won't be able to look themselves in. This will also won't be able to look at itself. But still, future information not leaking. Or the other, well, maybe you can even have this. This is the trick a lot of people use these from some time. Like you can actually have a band like this. So nothing here, all negative infinity. And you only allow this part. So this part, what this means is you're only allowed to look at yourself and the immediate previous token. Allow yourself an immediate previous token. Allow yourself an immediate previous. Kind of like running a kernel, like in a CNN, like you have 3x3 kernel like sliding around, right? Kind of like that. You're only able to look at immediate past. And this will actually save a lot of memory because you won't need to store all these. You will only need to store like only a band. So this is kind of like memory efficient, computation efficient. So people use this kind of trick to make the transform more scalable. In the past, I'm not sure people still do this these days. So this is not true. Not true. In the encoder decoder attention component, the output vectors from the encoder act as query and key vectors. Not true, because I've said it multiple times. The output vectors from the encoder act as key and value vectors. Query is coming from the decoder side in the encoder decoder attention. So hopefully everybody got at least didn't choose this because I've said it multiple times. So the correct answer is what? It's 1, 2. It's 1 and 2. Yeah, it's 1, 2. Right. So now it's time for practice session.